I realized there was some confusion about some of my terminology from the review session yesterday, and I wanted to go over what I meant by time t equals 0 minus and 0 plus and 0. I used the terminology that my instructor used when I took circuits, and I'm really sorry I can't be in class with y'all because it may sound like, I'm saying we're saying different things, but we're really saying the same thing, just might be saying it in different ways. So I wanted to explain what I meant by that. Also, my cat may come in here and join me. He was sitting on the keyboard, and he changed my font to Greek, as you can see up here by my tab. Yeah. So anyway, all right. So let's go back, all the way back to the beginning of Calc 1. And you would have a function, and maybe you would have a function that looked like this. And you would be asked for the limit, and let's say that's 1, 2, 3. The limit, and this is the t-axis, as t approaches 0 from the left of whatever this function might be. Let's say it's voltage. And as you approach from the left, you would say, well, the limit as t approaches 0 from the left is 3. Or you might be asked, what is the limit as t approaches 0 from the right? And in this instance, you would say it's 1. And so that's what I mean when I say 0 minus and 0 plus. But specifically, when we're talking about inductors and capacitors and transient circuits, we're going to look at what that means. Now, I've noticed on my YouTube videos, like I'll have videos that are 30 minutes long, and like the average amount of time that someone watches one of my videos is less than a minute. So if you're one of those people, let me just jump to what you need to know. So if there is switch action at t equals 0, so at t equals 0 you flip a switch, then IL of 0, I'm going to say to find IL of 0, look at the circuit before switch action. To find VC of 0, look at the circuit again before switch action. Okay, so that's your key takeaway. If you want to find the current through the inductor at 0, look at the circuit before switch action. If you want to find the voltage across a capacitor at time t equals 0, look at the circuit before switch action. Now, here's why. So let's take a look. These are the you can count on these things being true. The current through an inductor cannot change instantaneously. Now, through an inductor, the voltage can. You can have one voltage on one side of 0, and you can have another voltage on the other side of 0. In other words, if this were an inductor, this would be a perfectly acceptable graph, that you would have a discontinuity here, that you'd have a voltage on one side, and then you would have a voltage on the other side, if this was an inductor. You could not have this for a capacitor, and if this is current, this would not be acceptable for an inductor, because an inductor has to have continuous current. The graph for the current for an inductor has to be continuous. It can't change instantaneously. Similarly, the voltage across a capacitor cannot change instantaneously. So if I have two graphs here, so this is, let's say this is voltage, and this is current, and I were to ask Could this be the graph of the voltage across a capacitor right here? This is time. Could this be a capacitor? And your answer would be no, it cannot be a capacitor because you can't have this discontinuity. Could it be an inductor? It could be an inductor. Okay, and then over here, if I look at current, I'm just going to go ahead and say this is an inductor. Well, if this is an inductor, then that means that it has to be continuous. I cannot have a discontinuity here. If I had a discontinuity, it could not be an inductor. So, what does this have to do with when I'm saying 0 minus and 0 plus? Alright, so let's say I have a circuit. This is going to be a switch at t equals 0. And I want to find, let's say this is 12 volts, always a good voltage. Let's say this is 2 ohms. And how about 0.5 farads for my capacitor? And let's say that my job is to come up with the voltage across the capacitor. Oh, let's say my job is to find the energy stored in the capacitor at time t equals 0.5 seconds. Okay, so what I know is that I have my energy is 1/2 CV squared. I also know that I have derived a nice equation that I can use to find the voltage across a capacitor at any time in an RC circuit if I can reduce it to its Thevenin equivalent circuit. And that equation that we have derived by solving the differential equation that describes that circuit gives us that Vc of t equals Vc at infinity plus Vc of 0 minus V at infinity e to the minus t over tau, where tau is the time constant. So, in order to use this, I have to find Vc at infinity and Vc at 0. And it's this Vc at 0 that I'm really talking about right now, because that's what y'all are having questions on. So, I have my circuit, I have two different circuits. I have one circuit before 0, and I have another circuit after 0. Which one do I use to find Vc of 0? Okay, so before 0, it looks like, and this is what I call 0 minus. So at t equals 0 minus, so right on the left-hand side of 0, my circuit looks like this. And my capacitor, having been in that situation for a long time, I will say it had been in that situation for a long time, is going to be an open circuit. Now, right after the switch, so this is what I would call at t equals 0 plus. Okay, so it just means on the other side of 0, my circuit looks like this. So I have switch action at t equals 0. But what I know is that the voltage across my capacitor cannot change instantaneously. Well, we have a direction for time. We say time goes from left to right, I guess, if that makes sense. Time is moving in the positive direction. And so if time is moving in the positive direction, then I have to look at what the state of the capacitor was before 0 to see what it's going to be after 0. Because it will be something before 0. So it will be something before 0, and it can't change instantaneously at 0 to become something else. So I have to look at what it was before 0. So in this particular example right here, where I have 12 volts here and 2 ohms here, my capacitor is in parallel with this resistor. Since it's in parallel with this resistor, it has to have the same voltage as the resistor. And in this instance, the voltage is 12, because there's nothing else it could be. But, I mean, if we say this is ground, that's 0, the other side is 12. I mean, all of the current goes through this resistor, so all the energy, gets dissipated through that resistor. So, well, or you say the voltage source and the resistor and the capacitor, they're all in parallel. So VC of 0 minus has to be 12 volts. Now, I'm saying 0 minus, although that has to be, it doesn't have any choice. It has to be the same as VC of 0. So you were saying in the SI session, I don't think we ever used the term 0 minus. And that's fine, because there is no difference. It has to be the same because it can't change instantaneously, so it has to be 12. Now, that would not be the case if we were looking at the current. For the current, we would have, well, yeah, actually we would. We would have something different. Yeah, we would definitely have something different on either side of 0. I'll look at that in a second. It's not going to help us answer this question, but it may describe some things for you. Okay, so we know VC of 0 is 12. Well, what about VC at infinity? This is at infinity, so this is after switch action right here. There's no more sources. So eventually any energy that was stored in this capacitor will be dissipated through the resistor, and since there's no sources left to recharge it, VC at infinity will be 0. Our time constant for an RC circuit is RC. In here, our Thevenin equivalent is pretty obvious. We just have one resistor, and it's 2 ohms. And we have our capacitor, which I said was 0.5 farads. And so my time constant is 1 second. So now, at what time can you say your transient is over? I don't know what y'all have used in class. Typically, people will say 5 time constants, because it's decaying. It's exponential decay. So after 5 time constants, after 1 time constant, 1 over e. After 1 time constant, you have 1 over e left of what you had when you started. So if we started with, in this instance, 12 volts, and we're getting down to 0 volts as we are here, and we have exponential, after 1 time constant, we only have about 1 over e as much as we had to start off with. It's about 37%, I think. Yes, so 37%. So at whatever this time constant is, I have 37% of what my original value was. And when do we say we're down to 0? Well, it's exponential decay. It's approaching, I don't know why I wrote 0 here. That's 0 here. Would we say, how close to 0 do we have to get? So 5 time constants is what most people use, but some people do use 3 time constants. Some people use 4 time constants. I'm not entirely sure what y'all have done in class. So 5 time constants is safe. So if you wanted to say at what time is the transient over, then I would say 5 time constants. So transient is over at 5 times 1 second is 5 seconds. Now, y'all may have used something different, so I don't, just be aware of that. Where was I going? I was trying to find the energy stored in the capacitor at time 0.5 seconds. So I have my time constant, I have VC of 0, I have VC at infinity. So I can now find VC at 0.5. VC at 0.5 is VC at infinity, which is 0, plus VC at 0, which is 12, minus VC at infinity, which is 0. E to the minus the time I'm looking at was 0.5 seconds, over my time constant, which is 1. or 12e to the minus 0.5. Get a calculator. 12 times e to the minus 0.5 equals 7.28 volts. Let's ask ourselves a sanity check here. Does that make sense? If my time constant is 1 second and I started with 12, after half a second, does it make sense that I would have about 7? And yes, that does make sense. So like, let's just say we've got this picture here. This is 1, and a half would be right here. Yeah, that looks pretty good for a rough graph there. Okay, so how much energy is stored then? The energy will be 1/2 times the capacitor, which I said that was 0.5 farads, times V squared. So that would be that squared times 0.5 and 26.5 joules.